Hi, my name's Adam Jacobs, and my partner is Nathan Ha, and we did our project on fluid simulation. So, a high-level version of our project is that in the beginning of the simulation, a large blob of fluid is created, and it falls to the floor of the simulation. And inside the simulation, there's boundaries, so it's kind of like a big box, and the fluid it stays inside the box. So once it hits the floor, it kind of spreads out and hits the walls, and then it behaves sort of like a fluid and kind of curls around. You'll see it in the demo, but it's pretty cool. And then after some time, the old fluid sort of disappears. And at the top of the simulation, after the big blob is dropped, there's sort of like this fluid generator that moves from the left side of the screen to the right side of the screen, and uh, it constantly drops fluid down. And also in our project, we have the frames per second being displayed at the top, and it's constantly updating. So, so how are we implementing our fluid simulation? We're using logic from the Navier-Stokes equation. This basically we created our functions based on the math from these equations. And the main parts of our fluid simulation is we have these three helper functions that sort of determine how the fluid behaves inside the grid. So a good way of looking at it is our simulation is kind of just one big grid, and inside of the grid, there's these cells or like kind of nodes, and each node holds like a value. And these functions basically uh, they change the values and they interact with each other in like neighboring cells, so it can behave more like a fluid. So we have the advect function, which traces through the velocity field to see where fluid comes from. And in order to oh no, sorry. It traces through the velocity field to see where fluid comes from in order to interpolate values from like one location to another location. So it's basically like neighboring cells are interacting with each other. The diffuse function, it spreads fluid evenly out over time to neighboring cells. So it's kind of like imagine you drop like blue dye inside a cup of water. It kind of diffuses throughout the whole cup, and the diffuse does that like inside a simulation naturally. The project function ensures that there's no divergence within the simulation. This is basically like it helps it follow Newton's laws where liquid isn't like created in too much or like dissolved too much, so it like helps avoid compression and divergence. Um, it also subtracts the pressure gradient from the velocity field, so the fluid flows sideways instead of piling up. So yeah,
So we're using the GPU to basically parallelize like all the functions that were just mentioned. So we're using CUDA.jit to basically turn the Python code that we wrote into a PTX, which like can be executed on the CUDA hardware. So the CPU implementation that we just talked about like did not work out of the box with CUDA.jit. So we basically had to actually rewrite a lot of stuff to basically use like more CUDA style code in order to like have it actually run. But then, so anyways, the GPU does all the calculations, does like all the calculations in parallel, and then when we and then right before we need to like actually display it to the screen, that's when we copy all the data back to the CPU. And yeah, so a big part of this project, I guess, was actually rewriting our original like CPU functions to work with CUDA. So yeah, first we implemented the CPU version of the Navier-Stokes equations, and then to optimize that, initially we used njit, which is basically at JIT, but with like one a flag enabled. I forgot which one. I think it was, I don't know. We'll cut that. After so then after we tried changing the njit to CUDA.jit and it didn't work. Like we just got compile errors basically. So then we rewrote a lot of stuff to use like the actual CUDA code, which is like has like thread indexing and all that stuff. And then finally when we got it to work, we then started adding like FPS counters and stuff to like so we can actually see what to compare. And then now I can do the demo, which I need to share my screen for that.
yep.
Okay. Uh,
Yeah.
Okay. So let's see. Right now, I'm on main. So right now, main is using CPU code. So just JIT, no CUDA. So I'm just gonna do CD, and then I'm just gonna run it. Takes a second. Yeah. So that's basically the simulate what the simulation looks like. Yeah, I'm gonna run for a little bit, but the FPS is around 70, I guess. And
And this
then
is with the n size 100. So we did
okay.
some other experiments, I think, with
Yeah, in our
different.
results we use different sizes of the grid as well to like experiment with how it scales. Okay, that's enough of that. Now we can go to I think now we can go to our GPU version of the code. So and basically I'll just run the same thing. So this one's using our GPU now. As you can see, the FPS is like probably more than double actually.
I think the other one was at around 70
Yeah, this
for the
one's like
80ish.
one
Yeah.
almost 160.
Yeah.
Yeah, so that's basically what it looks like. And then yeah, it just runs like this forever.
Yep. Okay. And as for our results, we got this. So for the CPU version of our code, the one with the ngit, um, for the resolution size or n size, grid size, whatever, of 50, we got frames of like upwards of 200, so, not 200, upwards of 300. So it's around like I think it's around 266 for the 50 resolution, and then for 100, it drastically drops to around 71 frames per second, and then when you go to 200, it goes down to 18. And then looking at our CUDA version that was run on the GPU, the frames per second on the 50 resolution, it kind of didn't go as high as we were expecting, but it was still like pretty high. And then when we go to 100, instead of dropping like the CPU one did, it was actually the highest at around 163 frames per second. And then bumping up the resolution to 200, we got around 156 frames per second, which uh, it's pretty interesting to see how the GPU stayed consistent throughout all the resolution sizes. And then for fun, we did one with without any optimization, no just-in-time optimization on the CPU, and it was night and day. The frames were barely being generated, and although we put 0 for the 200 one, I think it actually was updating, but it was probably around 1 frame every 10 seconds. So, and then here's another way of looking at it, bar graph here. So yeah, it was around 267 for the NGIT CPU, and then the GPU stayed around the same. So yeah.